Hi everyone, this is Joy Canon and I'm with Sir Christian C. We're gonna discuss Graph Database and New SQL. Starting with Graph Database, I'm gonna do my very best to cram into 8 minutes discussion to give you context on graph databases. What is a graph? It's not the column chart or anything like that, but it is a node-to-node structure under the classification of NoSQL databases. NoSQL stands for not only SQL, obviously it is non-relational. It has the ability to run on large clusters, schemaless, and most of NoSQL databases are open source. It is known also as the 21st century web. Okay, so it does not consist of tables and entries like the relational database management systems. A graph is just a collection of vertices and edges, or in less intimidating language, a set of nodes and relationships that connect them. Graph databases store data as graphs, not rows and columns. We have open source tools, Neo4j, Infinite Graph, and OrientedDB. We have also here the websites that use graph databases for their storage: LinkedIn, Facebook, Google, NSA, and Pinterest. So if the structure of your database is more important than the data itself, the best choice for you is using graph database. But not all data can be modeled in graph. Example, spreadsheets, rows, and columns are better in relational database management system. In this social graph example, we have a couple of nodes here. We have the social media user at the center, some of our friends, the things she likes, watch, and stuff she does. Now, rather than just have a table of this user and all of her activities, we have nodes for the different kinds of things she can do. She can work something, she can watch something, she can be a friend with someone, and have a relationship for all of these nodes. Okay, when she watched something on Netflix, a relationship is created between her and Netflix. Maybe it's a movie with a time or a rating. So I hope you understand the concept of graphs using this simple paradigm. Okay, moving on to the next slide. How does a graph differ from a relational database? In ADBMS data structure, rows and columns are used in the data. But in graph database structure, we have nodes, vertices, and edges. In the relational database management system, table structures never change without a conscious decision. A database design is provided ahead of time. It's very difficult and complex to change the structure once the application is done. But in the graph database, the structure is constantly changing and it's not a problem as nodes and edges are inserted and updated also. Looking at this example, we have a graph database data model. We have two nodes for the company and one node for a person. In a table, each row becomes a node in a graph database. Okay, so if we have many records, it is equivalent to many nodes. And rows in many-to-many tables become an edge between nodes or the relationship. For example, here we have a person connected to a company. We have a relationship of works in. And company has properties, name, sector, location. Same with the person with the properties of name, age, and job. Looking at this example, we can also, it is very easy for us to add another node or another nodes for in this model. Converting the same database design into a relational database structure, we have a person here and company tables and the associative table or the relationship of the two tables, the person and the company. Now, for example, we are trying to find all people working at Google. When relational model, we execute the following query, which could require probably 3 index lookups corresponding to the foreign keys in the model. So we have to look up for the person ID, we have to look up for the company ID, and we have to look up for the company name. So imagine if we have so many tables to join, so many queries to execute. So it's very complex and tedious to do. While in the graph database, with the same problem, we can only have one query that requires one index lookup. Then one index lookup will traverse relationships by dereferencing physical pointers directly. For example, here, uh, Google, node Google can be searched only once, and the connections or the persons can be easily located or can be easily retrieved by using its edges or the links. So if you're deciding what you're going to use in your project, in RDBMS, the structure of the data must be identified ahead of time, and this causes complexity or difficulty when you have to change the structure or to add something in the structure of your database. But in the graph database, it's very the design can be more optimized. In terms of scalability, we can measure uh, databases using by data complexity and data size. Data size, how we deal with data sets that are growing in volume but are sort of equivalent in nature. And data complexity, data that is increasingly messy, increasingly connected, increasingly semi-structured. So if you look at the model, we have the key value stores in the right hand, followed by the big table clones, document databases, and all the way to the top, we have the graph databases. So graph databases are amazing at handling complexity. So if you have a domain that is very rich, highly connected, semi-structured, this is the best choice for you. But it's more challenging to handle graph database with large dataset size. And it has 90% of use cases. Moving on to the next slide, we have the power of graph databases. We have identified three: performance, flexibility, and agility. In performance, one compelling reason then for choosing a graph database is the sheer performance increase when dealing with connected data versus relational databases. In contrast to relational databases, where join-intensive query performance deteriorates as the dataset gets bigger, with the graph database, performance tends to remain relatively constant even as dataset grows. This is because queries are localized to a portion of the graph. Going back to the second, we have flexibility. So flexibility, graph databases differ in that the data is the structure. This provides a level in flexibility and resilience that is a great match for today's fast-moving business and agile development methods. So graphs are naturally additive, meaning we can add new kinds of relationships, new nodes, and new subgraphs to an existing structure without disturbing existing queries and application functionality. You can add any bits of data or on any nodes. For the third, we have agility. In particular, the schema-free nature of graph data model empower us to evolve an application in a controlled manner. Graph database development aligns well in today's agile and test-driven software development practices, allowing graph database-backed applications to evolve in step with the changing business environment. Graph databases are becoming very popular in real world. Here are some arenas where graph databases have found their use among the world's leading companies. So in the field of in PageRank, we have the Google. Google uses the concept of graph databases in calculating the order of displaying the results. In data management, the Cisco, one of the world's leading networking organizations, has recently adopted a hierarchical management system which is centrally based on the graph utility of the Neo4j database. And the most popular social networks, the Facebook, Twitter, and LinkedIn, are storing their connections in the form of graph databases as relationships. For network management, the telecommunications model their network, which consists of highly interconnected plants, customers, and groups. Adobe uses a graph database structure to link authentication details. Last is under bioinformatics. Bioinformatics Era 7 is a company that deals with DNA sequencing. Example, storing information on genes, enzymes, and other complex. So that ends my discussion on graph databases. So Sir Christian C will take over and will go on discussing the overview of new SQL. Okay.
Hi, this is Christian, and to continue with our report, I will discuss new SQL. Initially, SQL started with minimal user, with little money, and application programs are mostly open source. As technology and information became easier to access, there were more users, but database optimization was greatly sacrificed. Presently, there are plenty of users and more complex transactions involved in data warehousing, online transaction processing, as well as social networking. Thus, storage failure and efficiency was a major concern. Looking at the workload characterization from OLTP or online transaction process to social networking to data warehousing, you can see that transactions are becoming more complex, and from writing or a simple logging in of users to accessing and reading the database. So what are the new requirements of a database? To name a few, it should be a large-scale system with huge and growing datasets, can accommodate 9 million messages per hour, like in Facebook, 50 million messages per day, like in Twitter, high transaction rate generated by devices, especially mobile devices, high concurrency requirements to access the database, and transactional integrity and security. The solution is your new SQL. Let us define new SQL. Based on 451's group definition, it is a DBMS that delivers the scalability and flexibility promised by NoSQL while retaining the supports for SQL queries and/or ACID or to improve performance for appropriate workloads. ACID, atomicity, consistency, isolation, durability. Adopting NoSQL, these are some of the ideals of NoSQL, such as horizontal scaling, adding more nodes to a system, such as adding a new computer to a distributed software application. Thus not a relational model, it's schemaless, which allows you to store any data that you like. Based on Michael Stonebreaker's definition, SQL as the primary interface, ACID support for transactions, non-locking concurrency control, thus allowing and managing simultaneous access and connection to the data without locking it, hypernode performance, scalable, shared knotting architecture, where each node has its own mass storage as well as main memory. Michael Stonebreaker is a pioneer of database research and technology for more than a quarter of a century. He was the main architect of the Ingress Relational DBMS, the Object Relational DBMS Postgres, and the Federated Data System Mariposa. He is the founder of 3 successful Silicon Valley startups whose objective was to commercialize these prototypes. It was also Stonebreaker who stated that new SQL can solve interactions of users and its DBMS and provide real-time analytics. Considering new web-based applications such as multiplayer games and social networking sites, developers need better DBMS performance and enhanced scalability. The web and smartphones greatly increase interactions between the users and its DBMS. The need for more OLTP, online transaction processing throughput, might be able to solve this. In addition, real-time analytics is becoming vital for the survival of organizations. New SQL, a shared nothing architecture, means that there is a single point of failure. Each node is independent and self-sufficient, no shared memory or disk, scale infinitely, data partitioning where data are placed in various databases or servers, slow multi-shards requests where databases are multi-partitioned, thus significantly improves database performance. New SQL as column-oriented DBMS means that content are stored by column rather than by row. Efficient in hard disk access, good for sparse and repeated data, higher data compression, more reads, writes for large records with a lot of fields, better for relatively infrequent writes, lots of data throughput on reads. Traditional DBMS overheads are the following traditional overheads: buffer management, logging, locking, index management, batching, and useful work. Removing these overheads and running the database in main memory would yield orders of magnitude improvements in database performance. Since NewSQL adopts an in-memory storage, it can achieve higher throughput that facilitates quick insertion and quick response time. Low latency, which means avoiding delays in processing changes in the database. No buffer management, it's a key component in achieving efficiency. The buffer manager manages the functions for reading data or index pages from the database disk file into the buffer cache and writing modified pages back to disk. If serialized, no locking or latching. Locks assured logical consistency of data. Latches are like locks for RAM memory structures to prevent concurrent access and ensure serial execution of kernel code. An example of an ideal OLTP would have the following characteristics such as main memory only, no multiprocessor, high scalability, high availability, automatic configuration, fast, repetitive, and small. Fast means sub-second response time. Repetitive and small, interactive transactions that are frequent yet small. These are some new SQL categories based on new approaches, new storage engines, and transparent clustering. We have VoltDB, Clustrix, NoDB for new approaches, TokuDB, ScaleDB for storage engines, and scale-based DB shards for transparent clustering. In conclusion, new SQL is an established trend with a number of options, but it's hard to pick one because they are not on a common scale. It is not a silver bullet or it's not a quick solution to a difficult problem. Its growing data volume requires even more efficient ways to store and process it. That's all. Thank you very much.